Good day, this is Professor Will, CBMD PhD. Today's Sunday, June 21st, 2020. It is 8:07:19 seconds p.m. Eastern Standard Time, and today's self-quote and research. So let's get started here. Today's self-quote: no labor, no love, no money, no honey. You ever notice when you meet a girl, her first interest is in your work, wallet, and how much salary you make? Be wary. Women only come out of the woodworks when you got a car and money. Women would rather spend time with a bad apple that has money than a gentleman with brains such as myself. Money wins every time, in comparison to a decent lifestyle and a man with a brain such as myself. Most women who go for a man with a car, and all money and no brains, are the likelihood of every outcome. Be prepared and be wary.
Are planets with oceans common in the galaxy? It is likely scientists find. Date June 19, 2020. Source NASA Goddard Space Flight Center. Summary. Several years ago, planetary scientists began to wonder whether any of the more than 4,000 known exoplanets, or planets beyond our solar system, might resemble some of the watery moons around Jupiter and Saturn. Though some of these moons don't have atmospheres and are covered in ice, they're still among the top targets in NASA's search for life beyond Earth. Saturn's moon Elucidus and Jupiter's moon Europa, which scientists classify as ocean worlds, are good examples. Plumes of water erupt from Europa, and Enceladus, so we can tell that these bodies have subsurface oceans beneath their ice shelves, and they have energy that drives the plumes, which are two requirements for life as we know it. A NASA planetary scientist who specializes in volcanism and ocean worlds. So if we are thinking about these places as being possible habitable, maybe bigger versions of them in other planetary systems are habitable too. Hypothetically, there are planets similar to Europa and Elucidus in the Milky Way galaxy. And could they too be geologically active enough to shoot plumes through their surfaces that could one day be detected by telescope? More than a quarter of the exoplanets they study could be ocean worlds, with a majority of possible harboring oceans beneath layers of surface ice, similar to Europa and Elucidus. Additionally, many of these planets could be releasing more energy than Europa and Elucidus. Scientists may one day be able to test predictions by measuring the heat emitted from an exoplanet or by detecting volcanic or cryovolcanic liquid or vapor instead of molten rock, eruptions in the wavelengths of light emitted by molecules in the planet's atmosphere. For now, scientists cannot see many exoplanets in detail. They are too far away and too drowned out by the light of their stars. By considering the only information available, exoplanet sizes, masses, and distances from their stars, scientists can tap mathematical models and our understanding of the solar system to try to imagine the conditions that could be shaping exoplanets into livable worlds or not. While the assumptions that go into these mathematical models are educated guesses, they can help scientists narrow the list of promising exoplanets to search for conditions favorable to life so that NASA's upcoming James Webb Telescope or other space missions can follow up. Future missions to look for signs of life beyond the solar system are focused on planets like ours that have a global biosphere that is so abundant it is changing the chemistry of the whole atmosphere. Within the solar system, icy moons with oceans, which are far from the heat of the sun, still have shown that they have the features we think are required for life. To look for possible ocean worlds, a science team selected 53 exoplanets with sizes most similar to Earth, though they could have up to 8 times more mass. Scientists assume planets of this size are more solid than gases, and thus more likely to support liquid water on or below their surfaces. At least 30 more planets that fit these parameters have been discovered since researchers and their colleagues began their study in 2017, but they were not included in the analysis, which was published on June 18th in the Journal of Publications of Astronomical Society of the Pacific. With their Earth-sized planets identified, researchers and their teams sought to determine how much energy each one could be generating and releasing as heat. The team considered 2 primary sources of heat. The first, radiogenic heat, is generated over billions of years by slow decay of radioactive materials in the planet's mantle and crust. That rate of decay depends on the planet's age and the mass of the mantle. Other scientists already have determined these relationships for Earth-sized planets. The research teams applied the decay rate to their list of 53 planets, assuming each one is the same age as its star and that its mantle takes up the same proportion of the planet's volume as Earth's mantle does. Next, the researchers calculated heat produced by something else, tidal force, which is energy generated from the gravitational tugging when one object orbits another. Planets in stretched out or elliptical orbits shift the distance between themselves and their stars as they circle them. This leads to changes in the gravitational force between the two objects and causes the planet to stretch, thereby generating heat. Eventually the heat is lost to space through the surface. One exit route for the heat is through volcanoes or cryovolcanoes. Another route is through tectonics, which is a geological process responsible for the movement of the outermost rocky or icy layer of a planet or moon. Whichever way the heat is discharged, knowing how much of it a planet pushes out is important because it could make or break habitability. For instance, too much volcanic activity can turn a livable world into a molten nightmare, but too little activity can shut down the release of gases that make up an atmosphere, leaving a cold, barren surface. Just the right amount supports a livable wet planet like Earth, or a possible livable moon like Europa. In the next decade, NASA's Europa Clipper will explore the surface and subsurface of Europa and provide insights about the environment beneath the surface. The more scientists can learn about Europa and other potentially habitable moons of our solar system, the better they'll be able to understand similar worlds around other stars, which may be plentiful according to today's findings. Forthcoming missions will give us a chance to see whether ocean moons in our solar system can support life. If we find chemical signatures of life, we can try to look for similar signs at interstellar distances. When Webb launches, scientists will try to detect chemical signatures in the atmospheres of some of the planets in the TRAPPIST-1 system, which is 39 light-years away in the constellation Aquarius. In 2017, astronomers announced that this system has 7 Earth-sized planets. Some have suggested that some of these planets could be watery, and researchers' estimates support this idea. According to the researchers' calculations, TRAPPIST-1 E, F, G, and H could be ocean worlds, which could put them among the 14 ocean worlds the scientists identified in this study. The researchers predicted that these exoplanets have oceans by considering the surface temperatures of each one. This information is revealed by the amount of stellar radiation each planet reflects into space. A research team also took into account each planet's density and the estimated amount of internal heating it generates compared to Earth. If we see that a planet's density is lower than Earth's, that is an indication that there might be more water there and not as much rock and iron. Researchers say that if the planet's temperature allows for liquid water, you've got an ocean world. But if a planet's surface temperature is less than 32 degrees Fahrenheit, 0 degrees Celsius, where the water is frozen, then we have an icy ocean world, and the densities for those planets are even lower. Spacecraft get a boost in aerogravity-assisted interactions. New research examines the effect of rotation and other variables and the applications of aerogravity-assisted maneuvers to obtain an energy boost for spacecraft. Date June 18, 2020. Source Springer. Summary. Researchers mapped the energy variations of the spacecraft orbits due to aerogravity-assisted maneuver, a technique in which energy gains are granted to a spacecraft by close encounter with a planet or other celestial body via the body's atmosphere and gravity. In 2019, Voyager 2 became the second human-made object to leave the solar system, following its counterpart Voyager 1. Energy to carry these probes was obtained via interactions with the solar system's giant planets, an example of a pure gravity-assisted maneuver. The topic approached by the paper is one that has been tackled from a number of different angles before, but the team took the novel approach of considering a passage inside the atmosphere of a planet and the effects of the spacecraft's rotation as it performed such a maneuver. During the course of simulating over 160,000 AGA maneuvers, around the Earth the team adjusted parameters such as masses, sizes, and angular momentum to see how this would affect the drag on the spacecraft, thus changing the amount of energy imparted. The researchers discovered that the larger the values of the area to mass ratio, A divided by M, the inverse of the area density that they employed in their models, the greater the drag was on the probe. And thus the greater the energy loss it experienced due to this drag, and the lower its velocity was a result. But it may increase the energy gains from gravity, due to the larger rotation of the velocity of the spacecraft. The same effect also increased the region in which energy losses occurred whilst simultaneously reducing the area in which maximum velocity can be achieved. Their results indicate that as this is the inverse of area density, and density falls off at greater altitudes, drag can be reduced by a trajectory that brings a craft in at higher altitudes. This can eventually approach the values of trajectory given by a pure gravity-assisted AGA. As the Voyager missions show when performed at maximum efficiency, AGA maneuvers have the potential to send mankind beyond the reaches of our solar system, into the wider galaxy.
Good day, this is Professor Will, CBMD PhD on infectious disease, molecular microbiology, and astrophysics. Well, hope you enjoyed listening. Until next time, have a great day.